In this video, we want to calculate the pH of a solution of the weak base aniline. Aniline has the chemical formula C6H5NH2. And if we draw its chemical structure, we have a benzene ring attached directly to a nitrogen atom with two hydrogens. One way to think of aniline is as a substituted ammonia, where we replaced one of the hydrogen atoms of ammonia with a benzene ring, which in organic chemistry we call a phenyl group. In organic chemistry, you will learn that one of the effects of this benzene ring is to withdraw electron density from the nitrogen, therefore making it a much weaker base than ammonia. And with that in mind, to solve the problem, we need to know the Kb for aniline. And we see that the Kb is 4.2 times 10 to the minus 10, which makes it, yes, very much weaker base than ammonia. For the particular problem that we're going to do, we want to set the concentration of aniline to be 0.050 molar. And then we're going to use the fact that aniline is a weak base and use the principles of equilibrium to calculate the pH of this solution. When aniline dissolves in water, we have the following equilibrium. There we have aniline, and it dissolves in water. And since aniline is a base, it's going to accept a proton from the solvent water. And since it forms OH minus hydroxyl group, again we recognize that we have a base. So what we want to do in this particular case is to let X equal the equilibrium concentration of hydroxide ion. Now we also notice that whenever aniline dissolves in water, for every one hydroxide ion that forms, we also form one anilinium ion. So we can also use X to represent the concentration of the anilinium ion. With that in mind, we can now write the equilibrium constant Kb for this reaction. Recall that the products always go on top. And the reactants go on the bottom, so long as they are not pure liquids or pure solids. So we need to put the aniline in the denominator, but we do not put the water. And we know that this particular value is going to be equal to 4.2 times 10 to the minus 10. Immediately we can use the fact that we've already set the variable X equal to the hydroxide concentration and the concentration of the anilinium ion, so that we get X times X. And then the concentration of aniline in the denominator is the equilibrium concentration of unreacted aniline. So that's going to be equal to the initial concentration of the aniline, which we saw was 0.050 molar, minus a small amount of aniline that's going to react with water and become protonated. So now we've set up our basic equation that we want to solve for this particular situation. Because aniline is a very weak base, we can assume that the amount of aniline which reacts is very much smaller than the initial concentration. So therefore, we can make the assumption that the amount of dissociated hydroxide of aniline is very much smaller than the initial concentration. So we can assume it's going to be much, much smaller than 0.50 molar. And later on in the problem, we're going to go back and verify that that is a true statement. But if we do make that particular assumption, that converts our equation for Kb into x squared. Recall that we had x times x. And now the denominator is simply going to be 0.050 molar. And this value is equal to the literature value for the Kb of aniline, which is 4.2 times 10 to the minus 10. We can multiply through both sides, and we get that x squared is going to be equal to 0.21 times 10 to the minus 10th power. To solve for x, we need to take the square root of each side. If we do so, we recognize that the left-hand side becomes simply x, since we are only interested in the positive square root. And this is equal to the square root of 0.21 times the square root of 10 to the minus 10 power. What is nice about doing it this way is we can write down the square root of 10 to the minus 10 on site. We don't even need our calculator for that. And that is simply going to be 10 to the minus 5th power. And the square root of 0.21 is going to be 0.4583. And then we can convert this more neatly into scientific notation as 4.583 times 10 to the minus 6th power. At this point, we want to check if our assumption was legitimate. You want to check if that's true. So to do that, we want to find the percentage of X divided by the initial concentration of the aniline. So to do that, the initial concentration of aniline was 0.050 molar. And we determined from our calculation that the concentration X, the small amount of the aniline that actually reacted with water, turned out to be 4.583 times 10 to the minus 6th. And if we want to convert this to a percentage, recall that we always have to multiply this by 100% to make it a percentage. We can also do some manipulations of these values to make the calculation even quicker. So we can keep the numerator the way it was, 4.583 times 10 to the minus 6th. And then we can convert the denominator also into scientific notation as 5.0 times 10 to the minus 2 power. And then the trick we want to use here is to write 100% as a power of 10, and we can do that as 10 to the 2nd power percentage. If we do the manipulations here, we recognize that we're going to get a value of 0.91 times 10 to the minus 2nd power percentage. And we notice that this is much less than 5%. And 5% is our reasonableness limit, if we have a value of x that is greater than 5% of the initial concentration, then our assumption that x is small relative to the initial concentration is incorrect. So we couldn't use it. But in this case, we see that it works out. So put a check mark that our assumption was legitimate in this case. Recall that we had just calculated that the value of x was going to be 4.583 times 10 to the minus 6. But also recall that this variable represents the concentration of hydroxide, not the concentration of hydronium ion, or of H+, because we're dealing with a base here. So you have to keep this in mind in our next step when we calculate the pH. There are a couple of different ways we can do that. One way I want to demonstrate here is to use the definition of the pOH. So just as we have a definition for pH, we have a definition for pOH. It is the negative log of the concentration of hydroxide ion. So in this particular case, it's going to be the negative log of 4.583 times 10 to the minus 6. As we have done previously, we can break this up into two logs. We have minus the log of 4.583 minus the log of 10 to the minus 6 power. Part of the reason for doing this is that the log of 10 to the minus 6 we can immediately write down as minus 6. The minus in front changes the sign so that we get a plus 6 here. And the only thing we need to look up in our calculator is the logarithm of 4.583. And if we see that, we notice that it's going to have the value of minus 0.661. So that the pOH is calculated to be 5.337. Now be careful, because that's the pOH. And if we were to assume that this was the pH, we would have a problem right away, since we realize that we're dealing with aniline, which is a base. And we'd assume that an aqueous solution of a base should have a pH above 7 and not below 7. At this point, we want to use the relationship that the pH plus the pOH at 25 degrees C is going to be equal to 14. Therefore, we can calculate the pH as 14 minus the pOH. So we get that the pOH will be 14 minus 5.337, which gives 8.66. And we realize that in our initial conditions, the concentration of aniline had two significant figures, and the Kb value had two significant figures. So therefore, we want to round our pH to 8.7. Since 8.7 is larger than 7, this seems reasonable and consistent with a situation where we have a weak base. Thank you for your attention. Have a good one.